All right, let's try to finish this last worksheet for today's class. So we are going to review logarithmic differentiation and implicit differentiation in the context of multivariable derivatives. Okay, for the first one. In fact, it's not necessary to use logarithmic differentiation, but just for the review purpose. Okay, so let's look at how we are going to actually solve the problem. So f of x, y is equal to y to the power x, right? So we're going to take the derivative. So derivative over here on y to the x and take the derivative. Remember, this is going to be by the derivative formula. We remember that ax derivative is a to the x and the log a. So this one over here is y to the x and log y. Okay. Now you may say you haven't used logarithmic differentiation. This is how you use it. Say z is equal to y to the x, right? So log z is equal to yx to the log y, right? That's what we have. All right, so now we take the derivative both sides with respect to x. So now we have 1 over z dz dx is really partial, which is equal to log y, right? So partial z, partial x is equal to z times log y, and that's, you plug it in, that's y to the x times log y. That's called logarithmic differentiation. You take logarithm first and then take the derivative. Okay, just remember it's partial derivative. Now, how about fy? That's going to be easier because what we have now is y to the x. Take the derivative respect to y. This one is respect to x, right? So this is going to be simply x and y to the x minus 1. Okay, so the formula we are using is that if you take the derivative, that's a y to the a minus 1. All right, this is number 1. Number 2, partial derivative. It's implicit because e to the power z over there. And when we take the derivative with respect to one variable, it doesn't make any difference. So we're going to do e to the z, take the derivative with respect to x. That's going to be x, y, z, derivative with respect to x. Okay, so now e to the power z is still going to have e to the power z. And the derivative, you can write down zx, right? That should be fine. And then on the right-hand side, you have a product. Remember, y is a constant. That's fine. But x and z, they are both functions. So if you take the derivative of xy, you're going to get y. And then z is unchanged. And then plus xy, and then derivative of z respect to x, right? So that's the product rule. And then you see this is the one you want to find. So move them together, e to the power z, zx minus xy, zx, and that's going to be equal to yz. Factor e to the z minus xy out, and then you have zx is equal to yz, and we can write down eventually this is partial derivative with respect to x, and that's going to be yz over e to the power z minus xy. That's what we have. Now, we are supposed to do the second one, partial z, partial y. But I think I'll leave that to you to do because it's completely symmetric. In fact, by symmetry, we can say by symmetry, we have partial z, partial y is equal to xz e to the z minus xy. You can easily verify. Okay. Now the last one, we have triple derivative. But fortunately, this function isn't too bad. And let's first find gr. That's the derivative with respect to r. So we get this e to the r and sine st. There's no change because sine st is a constant. So this is going to be still the same. And now we're going to look at GRS. That's going to be e to the r. We're going to finish the one. So derivative sine is cosine st. But remember the chain rule. So we have t over here. And then we're going to have the triple derivative. Okay, so this is going to be e to the r. But now we have a product. So we're going to have, let's take the derivative of t first. We have cosine st. Okay. And then plus t. Derivative of cosine is negative sine st. And remember, we are taking derivative with respect to t, so we have an additional s over here. And just rewrite, not exactly simplification, but make it nicer looking. Okay, so minus st and sine st. And that's it.